Good evening, everyone. Gerald, John, you there?
We're here.
We're here.
Oh, nice
Oh.
to see you.
We're here, but we're not there.
Yeah, we're
Right.
here, but they're not there. Exactly.
And neither are you, as a matter of fact.
Yeah, I have a picture of there behind me. That's the best I could do tonight. So, for those of you who haven't figured it out already, we have 100% humidity up at the Chabot Space and Science Center. So,
It's
as
raining.
you know, yeah, it's pretty much raining, or it's the equivalent of it anyway. So it's
heavy mist.
Yes, not a very good night for us to be using telescopes, but that doesn't stop us, and we'll have fun for the next hour anyway, with news from the universe and photos from Nellie and other news from Chabot. But before we get started, I want to remind everyone that we are not yet open at the Chabot Space and Science Center, not open to the public yet. That is planned for November. And for those of you who don't know this, Chabot has become an official NASA visitor center. And that means we're going to have all kinds of new exhibits, and we're going to have more involvement from NASA in our presentations and our STEM opportunities and our exhibit refresh opportunities. So there'll be more on that later. We've already got new construction going on to make room for the new NASA exhibits. So there's a lot of exciting stuff coming up, and we're no longer in hibernation mode, but we're actually all actively working to prepare the Science Center for its reopening in November. So stay tuned for more information on that. We do still depend on donations, though, because we don't have the traffic coming in the door every day. And for those of you on Facebook, if you're so inclined, there is a donation button you can hit, and that would help us out. For everyone else, visit chabotspace.org, and there are ways to become Chabot members or to make one-time donations as you see fit. So thanks for that. I also want to do a shout out to Fremont Bank, who has been a regular sponsor of this program and other programs at Chabot. So thank you to Fremont Bank for your ongoing support. So what's on the agenda, Gerald? You had some photos you wanted to show, and maybe that's a good thing to start with, is what would we be looking at tonight? Yeah.
Did we say Happy 4th yet?
Oh, there we go. Of course. It was the explosions that I was listening to that made me forget. We live in Oakland, so
I mean, it is.
Yeah.
It's not the 4th here, but it is the 4th in New York. So
yeah. Well, actually, the 4th of July holiday in Oakland starts sometime in March. That's when the first shipment of fireworks makes it to the city.
Right.
And then we spend the next month reading about the confiscations of said fireworks. And so the game becomes, how many can we fire off before they get found and confiscated? So anyway, we've been listening to fireworks for many weeks now.
Or how many fires can we start?
Right.
Yeah, one of the joys of being up at the Chabot Space and Science Center this time of the year is you're up high looking down over the city, and you get to both watch and hear the fireworks going on. It can be pretty spectacular. So anyway, yeah, I've got a couple of things I thought we'd share. Since we can't actually view through the telescope, I thought we would share a couple of the things that we might be looking at or might have been looking at had we been able to use the telescopes. So if you bear with me here for a second, I'll figure out how Windows works. And not there. Oh, there we go. Let's see. Here we go. You see that?
Yeah, looks like M51.
M51. M51 is a spiral galaxy, actually similar in some ways to our Milky Way galaxy. It's pretty far away. It's 37 million light years away, and it's feeding on another galaxy, which is actually not uncommon. A lot of times spiral galaxies will absorb smaller galaxies nearby. The Milky
Seems
Way,
kind
in
of
fact,
cannibalistic to me.
yeah, the Milky Way has actually absorbed several small galaxies in the past, and there are a couple of dwarf galaxies near the Milky Way right now, the Large and Small Magellanic Clouds. Those will eventually be absorbed by the Milky Way also. One of the things that we've talked about in the past are globular star clusters. And globular star clusters, actually, the theory is that when the Milky Way galaxy was first forming, it was absorbing, this was almost 12 billion years ago. So the universe was a lot smaller, and the Milky Way was absorbing other smaller galaxies at the same time. And that actually caused large clumps of gas and dust that were in the process of forming stars within the spiral arms of the Milky Way to be knocked out of the spiral arms up into the region we call the halo. So that's why those globular clusters persist to today. But anyway, you see here in the galaxy M51 another galaxy being slowly absorbed. You can actually see here the material that's being pulled off of that galaxy into the much larger M51 galaxy. So anyway, that's one of the things we might have looked at tonight. Got a couple others here I can share with you. Let's see what else we got here. Bear with me just a second. Oh, yeah. Speaking of globular clusters, if I can get to it. Here we go. Very high up in the sky right now is the globular star cluster M13. It's in the constellation Hercules. M13 has at least 500,000 stars in it. Those stars are orbiting around the center of the cluster in highly elliptical orbits. So they go in close to the center and then they swing way out. And when they're far from the center, they're moving very slowly. And as they come in, they speed up, whip around the center very fast, and then head back on out. And so all these stars are orbiting like that. And then the cluster itself is orbiting around the galaxy in that region that I mentioned called the halo. So if you imagine the Milky Way galaxy is a kind of a flat disk with spiral arms in the disk. And then surrounding that flat disk is a more or less spherical, very nebulous region called the halo. There are not nearly as many stars in the halo, and what stars are there tend to be older stars, and that includes the globular star clusters. The globular star clusters can be easily more than 10 billion years old. Because they are out in the halo, they don't have a source of new gas and dust to form new stars. So all of the high mass stars that formed in globular star clusters have all already gone away. High mass stars have very short lifespans. And what remains are the stars with lower mass. Lower mass stars live much longer. So in order for a star to have lived at least 10 billion years and still be viewable, we know that that has to be a fairly low mass star. And that's true of most of the globular star clusters around the Milky Way. There are about 150 of them around the Milky Way. And we see them around other galaxies as well, like the Andromeda Galaxy and even M51 and
Hey, Gerald.
Yeah.
There's a really good question that Stephen asked. And within a globular cluster, what's the possibility of there being planets? I would think that it's lower probability than your typical star.
Right. These stars often get very close together. Just to give you an idea, the width of M13 is about a little over 100 light years. Now, if you think about stars around our sun, the closest star to our sun is slightly over 4 light years away. So if you had 100 light years and you were going to line them up every 4 light years, you'd only have 25 stars. But here we've got thousands of stars. So the separation between the stars is much less. They do bump into each other occasionally. They do collide, and certainly they gravitationally perturb each other as they get in, especially when they get in close to the center. So that does not bode well for planets, certainly planets that are far away from their host star. Planets that are close in probably have a good chance of surviving, but the ones that
I
are
would have to
farther
guess
away,
that there's at least some there, though, right?
yes, I would imagine so.
But what about the aspect of these stars? They're so old and they are so primordial in their composition, in the sense that they don't
Right,
have
right,
much in the way of heavier
very low,
elements. Wouldn't there
right.
be a shortage of material to create planets? Because there wouldn't be the rocky material in the
Well, you
same
could still
abundance
have gas
as in
giants.
other molecular clouds. Or-
That's possible, yes. But remember, we have some planets in our own solar system that are mostly hydrogen
Oh, true.
or
Right.
other
Okay.
lightweight gas,
Gas
like
giants,
Jupiter.
absolutely. Yeah.
Right,
I wasn't
right.
thinking
So,
gas giants. I was thinking rocky planets. Yeah, of course, gas giants
and
would
as
be
we
definitely possible.
and as we do exoplanet studies, what we're finding is there are actually a lot of stars out there that have gas giant planets orbiting very close to them. So if that's the case in this globular star cluster and in other globular star clusters, planets could still survive. They just, have to be close into the stars.
Well,
All right.
Thank you.
Okay, I got a couple of other things I wanted to show you, but with the telescope at Chabot, we get a lot of good photographs. Can you?
I think you're cutting out a little bit, Gerald.
Yeah.
Stop moving, Richard.
I think we lost Gerald.
I think we did.
Yeah, Tim mentioned that, and on follow up to Stephen's question.
You still hear me?
You're cutting out, and let's
your
try
video
again.
is frozen too.
And your video is frozen, so you might want to rejoin. Or yeah, there he goes.
Yeah.
Bye, Gerald. There he is.
I'm
You're
back.
Hey.
Right. One more time.
Yeah. Just as a follow up, Tim Thompson mentioned that he knows of an exoplanet discovery in M4, which is a globular cluster. So we have actually found exoplanet in a globular cluster. So there you go.
Yeah, there's no reason why they can't be there. They just have to kind of be close into a planet.
Yeah.
I mean, to a star.
There's nothing that gives you any idea about the statistics of how many there would be, or what sizes, or any of that kind of stuff.
Hey, I want to make a plug for Tim while he's already helping us with the with information for our program, as he often does. Tim is doing a Sunday night show on Facebook from Mount Wilson, not live telescope, but on the history of the Mount Wilson Observatory and the telescopes up there. And I think it's called Sunday with Tim or something like that. Anyway, Tim, post a link on Facebook.
Yeah, sounds good.
So that people can see it. You won't be competing with anything we're doing because we don't do anything on Sunday. So if it was on Saturday, we wouldn't have mentioned it. But the
oh yes, we would have.
Yeah. So anyway, I do want to mention that. Thank you, Tim. Go ahead, Gerald. Sorry,
Yeah,
I interrupted.
Just one more thing I wanted to share and do a little comparison here. So what I'm going to do is show you an image taken of M16, Messier 16, which is kind of in the heart of the galaxy, in the southern sky, as viewed from Chabot. And it's a very dense a region of very dense clouds where new stars are forming. So this is a huge star forming region that you see right here. Now, if you look at this, it may look kind of familiar. And the reason it looks familiar is because we've seen essentially the same object taken by the Hubble Space Telescope. But notice the difference in color. So we have the image as photographed by the Chabot Space and Science Center's 36-inch reflecting telescope. And then we have the image taken by the Hubble reflecting telescope. And they're very different in color. And the reason for that is this is a fake color image. This is a combined back. This is a real color image. So what the Hubble Space Telescope often does when they're processing their image, they use what they call the Hubble Palette. And the Hubble Palette, they take regions of their images and convert to colors to make details stand out more clearly. And, you know, one of the nice things about this image is that you can kind of zoom in, except that I can't get at my zoom button because there we go. So we can kind of zoom in a little bit. And a while ago I said this was a star forming region, and stars form within huge clouds of gas and dust. And what you don't see above the top of the frame, up out of the frame above, are some very young, very, very hot, high mass stars that recently formed. And they're so hot, they're putting out a tremendous amount of radiation, some of that in ultraviolet radiation. And radiation actually has pressure. And so what's happening is the pressure from that radiation from that young star is actually pushing the cloud away from it. But embedded in the cloud are other stars that are still in the formation process, lower mass stars still in the process of forming. And you can actually, if you look at this image carefully, you can actually see where some of those stars are. One's right there. There's one down here. I think there's another one right up here. So what's happening is those stars are still within a cocoon of gas. And the stars, because they have, strong gravity, they're trying to hang on to that cocoon, even as the gas farther away from the star is being blown away. So this is just a really cool picture. And this kind of detail is best seen in Hubble images because they use that Hubble palette concept where they recolorize things to bring out more detail. But there's still the great image. Yeah, I gotta zoom back in here. Come on, there we go. Yeah, you still get the great image. Oops, wrong direction. The great image taken by our 36-inch telescope at Chabot. We still see a lot of the detail, not as much as you do in the Hubble image, obviously. If we can move our telescope a little bit higher in elevation, we might get a little bit better imagery.
Like a couple hundred miles.
So anyway, those are just some images I thought I'd share. These are all things that are in the night sky right now. There is one last object that I wanted to share with you, if I can find it here. There we go. John, you're in the way.
What?
Yeah. It's just the way Zoom works here. Okay, so this is one last thing. The constellation Lyra is up pretty high in the sky right now. And in the constellation Lyra is an object called M57, also called the Ring Nebula. And this is a photograph of the Ring Nebula taken with our 36-inch telescope at Chabot. And the Ring Nebula is the remnant of a dying star. So we call these planetary nebulae. A planetary nebula has nothing to do with planets. It's a cloud of gas and dust that was shed by a star as it was reaching the end of its life. When a star like our sun, or any star less than about 8 times the mass of the sun, when it gets towards the end of its life, it swells up, becomes a red giant. It goes through several phases of expanding and contracting. But when it's a red giant, its gravitational hold on its outer layers is very weak. There's a lot of churning going on inside the star, which produces strong winds. And so the outer layers of the star are actually blown off the star out into space. And this goes on over thousands of years, actually tens of thousands of years. Eventually, whatever's left of the star, as it blows off its outer layers, you start exposing the inner part of the star. Eventually, the fusion process, which is what drives the star, the fusion process ends. What's ever left of the star collapses, becomes a white dwarf. White dwarf is very small, it's very dense and compact, and it's extremely hot, and it generates a lot of ultraviolet radiation, which goes out, and the white dwarf is surrounded by all that gas that it was expelling while it was a red giant, and the ultraviolet radiation ionizes the gas or excites the gas and causes it to glow. So we can see the white dwarf is barely visible at the center here, and this is all that gas that was thrown off by the star while it was still a red giant.
I'd like to mention that this type of thing, these planetary nebula, are very, very common. There are thousands of these things, but really there's only a dozen or 2 dozen that are large and spectacular from our view
and close
here
enough
on
to
Earth.
us.
And close enough to us.
Yeah.
You can see a lot of the other ones, and some of them you have to use special filters and, put the filter in front of your eye and move it away, put it in front, move it away to see if anything changes in your view. And you say, aha, that's getting brighter and dimmer and brighter and dimmer. That's the planetary nebula, and it's really just a dot in your telescope. So most of them are like that and not like this Ring Nebula just because of their relative distance. But this is a spectacular object.
The Ring Nebula is about 2,400 light years away. Mm-hmm. And like you say, there are a lot of them out there, different distances. They're all over the place. This is how, lower mass stars end their lives.
Yeah, there's a question: will the sun eventually become planetary nebula? Yes.
Yes, it will.
Yes, it will.
You're seeing a preview of what's going to happen to the sun in about 5 or 6 billion years. All right.
And they will be discussing it at Proxima Centauri.
Yeah, right.
It's some show much like ours.
Right.
Now, you think with all this going on that any planets that were orbiting around the star are long since gone. And that's sort of true. Planets that are orbiting close to the star or were orbiting close to the star when it was a main sequence star, when that star expanded, it got hundreds of times its original size. And so it would have engulfed those close in planets. But planets farther away, it's still possible that they're there. They still may be orbiting around that white dwarf star. And, it's not going to be very hot there anymore, but they could still be in orbit.
And the presence of those planets goes a long way to explain some of the variation in shape and structure of the gas clouds, because some of these planetary nebulas have very intricate, almost spirograph-like patterns in them, right? And there's no reason for those patterns to emerge simply because the gas is being blown off from a point source. Instead, the orbits of planets may be dragging those different gases around, and as it passes through different parts of the gas cloud, it causes perturbations that look like knots or look like twists and creates intricate patterns.
All right. Well, Richard, speaking of planets reaching the end of their lives, I think we had some news here. It's actually been a few weeks now, but It's still getting a lot of press attention. And so I think you wanted to talk about another exploding star or dying star, or however we want to say it.
Well, there was a few stories I thought would be interesting tonight. And are you talking about the supernova
Yes.
story?
Yep.
Okay,
Yep.
so we've discussed supernova frequently on our weekly program, and if you recall, there are two general types of supernova that we've discussed. There are what are called type 1 supernova and type 2 supernova. Now, type 1 supernova are caused by two stars that are in orbit around one another. And one of those stars would happen to be a white dwarf star. And a white dwarf star is very small, but very, very hot, consists of what's called degenerate matter. And the star that's next to it could be a more standard star, maybe much like ours, or maybe a red giant star, something more ordinary. And what happens is that the material from the neighboring star, from the larger star, sometimes gets transferred because of gravitation to the white dwarf. And it's quite kind of like putting gasoline on a fire. And what happens is it causes the white dwarf star to massively flare up and sometimes even destruct into what is called a type 1 supernova. And they're very bright, and we could see them occur not only in our galaxy, but we could see them occur in other galaxies. We know it's a type 1 because type 1 supernova have a particular brightness and particular set of signatures in their light that identify them as being that type of supernova. The more spectacular type of supernova, which is more rare, is a type 2 supernova. And a type 2 supernova is known as a core collapse supernova, which is caused by the star's material becoming more and more dense, possibly forming all the way to iron. And the star can no longer support itself. There's not enough heat, not enough outward energy for the star to maintain its shape. And it causes the star to collapse on itself. And that collapse causes a massive explosion. And you either end up with a neutron star as a remnant of that supernova, or you end up with sometimes even a black hole. And those stars that cause type 2 supernova are at least 10 times the mass of our own sun. They have to be really massive stars. And so all of the supernova that we have observed over the years and categorized have always fallen into either type 1, type 2, or some subset of type 1 and type 2. But there has been a theory for many years that there's a third type. And that third type is called an electron capture supernova. And we're going to maybe call that a type 3. I guess we could tonight. You heard it here tonight first. I'm calling it a type 3 supernova. And the electron capture supernova is a theory that is designed to explain supernova in stars that are not quite as massive as the ones I just described, maybe 7 or 8 times the mass of the sun. And they are still core collapse supernova, even though they're not massive enough or energetic enough to have been caused by a iron core. So what happens is the magnesium and neon elements in the star capture electrons. And those electrons, if they hadn't been captured, would have been supporting the star's size and structure. But now that they've gotten captured, it's like removing the tunnel supports for the star, right? The star loses the ability to maintain its size because these electrons, which are moving around really fast, are suddenly no longer there to create outward pressure in the star, and that causes a different type of core collapse. Maybe not quite as energetic as the type 2, but equally spectacular. And there is a supernova that appeared in 2018 called Supernova 2018 ZD, and it had all of the fingerprints of this theoretical electron capture. I keep forgetting the term, electron capture supernova. And there's also a lot of speculation that the Crab Nebula was an electron capture supernova. And I'll show a picture of the Crab Nebula, and then I have something interesting to say about that Tim Thompson reminded me of. Got to get Tim on the script writing for this
Right.
thing. So anyway, here's an image of the Crab Nebula, and this is known as M1. It's a Messier catalog object. It's a lot of fun to look at, and it's a beautiful object to photograph. Tim reminded me that supposedly back in what was it, 16? What was the year that the Crab Nebula was?
1054,
Or
1054.
1054, but it was supposed to be July 4th. At least so he says.
Yeah.
So this was the July 4th fireworks from 1054.
Is that on
it
a
may have-
Julian calendar? Or
on the, yeah,
well,
well, you can always find a calendar that will have it. Back then, there were lots of calendars. But in any case, this might have been the first known example of an electron capture supernova, because it has many of the elemental signatures of, at least theoretically, of what that would look like. So anyway, that's the new type of supernova. Maybe we'll get to see more of these.
All right.
We got a couple of questions.
Sure.
Larry asks, what gases give off what colors? Maybe Gerald, bring up your Ring Nebula photo again, and you can.
Yeah, that's a good one to use.
Okay, hang on just a second. All right, you see that? So
Yeah.
there's a couple of colors that stand out here. First of all, you see the red color on the outer part. That's caused by hydrogen. Remember how I said that the white dwarf is generating all this ultraviolet radiation? The ultraviolet radiation goes out and it excites the hydrogen atom. And the hydrogen atom has a proton in the nucleus, and then it has an electron buzzing around the nucleus. And the electron is normally at what we call a ground state, a low energy state. But when it gets hit by ultraviolet radiation, that pushes the electron into a higher energy state. And it's not a nice smooth process. It actually jumps from one energy state to another at certain energy levels. This is what we call quantum mechanics, because rather than just being a gradual increase in energy, it's like it goes from 1 to 2 without going 1 1/4, 1 1/2, and so on. It goes straight from 1 to 2. So anyway, it causes the electrons to jump to a higher energy level. Now, the electrons only stay at that energy level for a very short period of time, and then they drop back down. If an electron around hydrogen drops from the second level above the ground state to the first level above the ground state, it emits a red colored light that's like what you see here.
Want to mention that, Gerald, that even though it looks like there's just a little bit of the red around that, that's really the more abundant
right
element there. That's
right. This cloud is mostly hydrogen, and so if it was all hydrogen, then the whole thing would just be red like this. But also in this cloud is some oxygen. This star was obviously had enough mass to where the fusion process inside the star, as it got older, progressed to the point where it was producing oxygen. Oxygen, when it's hit by that strong ultraviolet radiation out in space, it can be what we call doubly ionized. It can lose 2 of its electrons. And when that happens, the oxygen glows in a very bright sort of turquoise color, which is what you see here. Now, it looks like that's mostly what's out there, but it turns out that the brightness of the oxygen, what we call oxygen 3, the oxygen has lost 2 of its electrons. The brightness of it is much brighter than the excited hydrogen. So the color dominates, even though it is not the dominant gas. The hydrogen is the dominant gas, but the oxygen, the ionized oxygen, glows much more brightly than the hydrogen gas does. So that's why it appears dominant. And when we look at other planetary nebulae, we see often 3 or 4 different colors within it, and that represents the chemical composition of the star as the gas that was blown off from the star is being hit by all that high energy ultraviolet radiation. All right.
Yeah, thanks.
Yeah.
So, speaking of photos, I got one to share here. So, I keep thinking that if I go to that ridge, I'll be able to look over it and see Barstow. But no, it is not. It is not California, although parts of California certainly look this way.
Especially now.
Yeah, especially now. This is the astro photo of the day, what we call the APOD, from July 1st. And it is the one of our more recent Mars spacecraft called Perseverance. And Perseverance's camera, not the one that we're looking at in this photo, obviously, it's the one that's taking the photo, it's the one that's at the end of the arm, is actually a very narrow field camera. It's not designed to take these wide landscapes. So what they did is they set it up to do a mosaic. And this is actually dozens and dozens of individual smaller framed photographs stitched together. And they programmed a movement pattern in the arm to basically just, travel around and then, go scan back and forth like this. And then they stitch together all those individual squares to create this beautiful landscape. It's a very high resolution camera. And it's taking a picture of itself and the little companion drone on the spacecraft that is sitting there waiting for. I don't know if it's going to fly anymore or not. I think it's done.
Yeah, it's done. Yeah. I believe 6 flights, and the 6th flight didn't go so well. So I think they're probably done.
Well, it's got a nice pose.
Yep.
Nonetheless. So I don't know how I feel about robots taking over the astrophoto of the day, but this isn't bad. This isn't bad. I think it's well deserved from the team at JPL to put this together.
There were still humans involved in processing the image for sure.
Or so they say.
Yeah. Hey, a good question. Stephen asks, is the star collapse in supernova an extremely fast event? So in astronomical terms, yes.
Yes. Yeah. The collapse, when a core collapse supernova happens, the collapse actually occurs inside the star. So if you were outside the star looking at it, you wouldn't realize that the interior is collapsing, because what happens, it starts at the center. And the fusion process that provides the outward pressure of a star dies at the center when it becomes iron 56. And so then there's no longer any pressure from the center to push outward. And so gravity takes over and it collapses, but it collapses from the inside first. And it collapses down and then it bounces, it rebounds out. And that's what creates the explosion, is that rebound, because everything just falls in at once, and it falls so vigorously that it just bounces off and rebounds. So the initial explosion is in minutes. But then it goes through a long process. It gets brighter and brighter as things are blown away. It gets very bright very rapidly. So just within a day or two, it reaches maximum brightness. For a type 2 supernova, the core collapse type supernova, it then slowly starts dropping off in brightness, but it reaches a plateau and it stays at that plateau for a few weeks, and then it starts to drop off again. So it actually takes a long time for it to fade out. The type 1 supernova that Richard was talking about, where you have the white dwarf pulling matter off of an adjacent red giant, that initially starts very similar. It ramps up very quickly, but then as it drops off, it does not have the plateau. It just slowly continues to drop off over a period of several weeks. So that's one of the ways we can distinguish between a type 1 supernova and a type 2 supernova, is by looking at the profile of how bright it gets and how it fades off over time.
So would you say that the core collapse process, the entire process, like when a star says, okay, I'm ready to start collapsing, right? I mean, we're talking decades, or at most, 100 years or a couple hundred years for that process, right? Or is it happening over a longer period when it starts the core collapse?
The core collapse happens within minutes.
Oh, did that collapse? It isn't something that's slow and then it does the bounce, and
No,
so the
it's
whole
very rapid.
collapses. I see. Okay.
Right. What's going on is you've got fusion going on at the core, and the fusion is what generates the energy that keeps the star expanding. Once the fusion reaches the point where I think it goes to nickel 56, and then it drops back through a decay process, it drops back to iron 56. Iron 56 can't be fused.
Oh, right. So it hit the
fusion
cul-de-sac at that point.
So
Yeah.
at that point,
Yeah.
it stops, and it stops very quickly.
I see.
And now you don't have that energy being generated at the core to cause the star to, the inward pressure or the outward pressure from the core to keep the star inflated. And immediately you start getting this collapse, and it happens very quickly, within a few minutes. And like I say, when you're outside of it, you don't realize it's happening until the whole thing blows itself up.
Wow, that's wild. I thought it was a much longer period of time for that exhaustion to take place, but it sounds like it just hits the limit and then goes all at once, which is quite amazing.
Yeah, you can be looking at a star field and all the stars look normal today. 2 days from now, there's this big, huge, bright thing, and that's the supernova.
Yeah. Thanks.
All right. You had some other stuff that you want to talk
about?
I
did, yeah. So there's some other news from this week. We every once in a while we mentioned the James Webb Telescope, and which is the next generation space telescope being launched by NASA, and we usually start cracking some jokes about it, like the James Webb Telescope, as it will always be the telescope of the future, or something like that, right? Because it's been delayed and delayed and delayed, and but this week it got its launch clearance. And what that means is they took a look at the requirements of the spacecraft, and they took a look at the characteristics of the launch vehicle, and they modeled what the launch would look like in terms of vibration and force on the telescope, and all of the details about basically, will the telescope survive the launch, is what the launch clearance is about. And it passed. So that means it's good for a launch right now on October 31st. It's going to be a Halloween event. And for those who aren't
Fingers
familiar
crossed.
with the Webb
That's
telescope,
kind of spooky.
it is spooky. The whole thing is spooky. For those of you who aren't familiar with the Webb telescope, it differs very much from the Hubble. The Hubble Space Telescope is designed to capture light in what we call the visual spectrum, right? Standard red, green, blue, with other science packages that deviate from that somewhat as well. But it's mainly visual spectrum instrument, and that's why we are able to enjoy those wonderful photographs because it's capturing light in the familiar RGB spectrum. The Webb telescope doesn't want to do more of the same, right? The idea behind the Webb telescope is, okay, in order for us to now make sense of what we've discovered with the Hubble telescope and other instruments here on Earth and other types of observatories that we've launched, we need to look even further back in time. And if we're going to do that, we have to look as much as possible in the red spectrum, in the elongated wavelengths of light that are the remnants of the earliest moments of the known universe. And in order to do that, we need a different kind of telescope, one that's sensitive to the infrared spectrum. And the Webb telescope is exactly that. Now, the thing about infrared is you really want it to be as far as an infrared telescope, you want it to be as far as possible from any type of light pollution. And you also have to have it in a very thermally cold environment so that, if infrared is starting to be more like heat than it is like light, right? So, the reason your car heats up is because of the infrared spectrum, right? So you've got to have it out in deep in space, away from light pollution, and as much in shadow from the sun as possible. And so the Webb is going to be in an orbit that is so far from Earth that we're never going to be able to service it. So they better get it right the first time. And because there's not going to be any missions to repair it. They lucked out with the Hubble. They sent a terribly flawed instrument into space, and then they were able to turn it into a heroic event by creating an optical package to fix it and then sending astronauts to install it. And it was all very cool, and it all worked, and we've gotten wonderful results over the years. If there's anything wrong with the Webb telescope, it's just going to be considered a disaster. Because
total
there's going
loss.
to be total loss. Total loss. It's got to work right the first time and every time. So it's probably fine that they've been very conservative about launching it, and that they're taking their time, because I think nobody wants to be the guy who's, oh man, he left the bolt out, or he forgot to put the battery in.
You're the nattering nabob of negativity, aren't you?
Well, and the deployment of the telescope itself is a very complicated process. It's not like it's something very easy to do or that we've done many times before.
I mean, I let me see if I can find a picture of the Webb
Somebody asked what the launch vehicle will be for the James Webb.
It's an Ariane rocket.
Right,
it's by the European Space Agency, and it's going to be launched from French Guiana in South America. That's where,
right on the border or on the equator.
Right on the very close to the equator.
Right.
Let me show a picture if I can of what this telescope looks like. It's quite remarkable looking. And let me share my screen. Can you all see that?
Yeah.
Yep.
All right. So the most notable thing is the color of the mirror. And the reason it looks gold is because it is coated with gold. The mirrors themselves are made of beryllium. They're metal. And I don't know if you guys ever picked up a piece of beryllium. Gerald, you probably have.
No.
It's brittle.
Well, what's amazing is you see this solid chunk of metal in front of you, and your mind says, okay, this is how much force I'm going to need in order to pick it up, right? You think it's going to be this heavy thing, it's
Yeah,
a slug
yeah,
of metal, and you
yeah.
pick it up, and it's like feather light.
Right.
It's a remarkable material. So anyway, these mirrors are made out of beryllium, and they're coated with gold. And gold is a particularly good coating for reflecting infrared light, and that's why they did it that way. So that entire mirror structure folds up in some complex configuration. And so they'll send it up in the spacecraft. They'll drop it into the Lagrange orbit, the stable orbit. It's actually orbiting the sun, not orbiting the Earth. And then it's supposed to all unfold properly, like an origami.
Yeah.
Yeah.
If you look
Yeah.
carefully, you can see that there's a bunch of hexagonal sections. There are actually 18 of them. The total diameter of the mirror is 6.5 meters, which makes it much bigger than the Hubble. And I believe the mirrors were either figured or polished at Tinsley Labs in
Yes, they were in Richmond, Richmond, California. Yep. And here, this was kind of crazy. They would do the polishing and figuring in Richmond, and they had special tables that they had to construct to do that work, because the vibration from the 80 freeway was enough to disrupt the polishing process. So they have these special vibration-free tables to prevent the freeway vibrations from affecting the polishing process. And then after they polish it, they had to send it all to Washington, D.C., and where they had the cryo lab to test the figure of the mirrors in 0 degree conditions, or 0 degree Kelvin conditions, right? And then if they found errors, they would have to send the mirror back to Tinsley, and where they would work on it some more, and then they would send it back to the East Coast for another round of testing. So there was a lot of logistics in getting this project done. So the fact that it took so long is not much of a surprise.
Did you say the 80?
Yeah, I'm from LA.
The 80, he's from LA.
I'm from LA. All freeways.
Okay, translating for those of you in Northern California and the rest of the country, he was referring to Interstate 80 or I-80.
Yeah, it's the 101, the 405.
No.
The 80.
You don't live down there anymore. You can clean up your language. And,
Hey,
actually,
about...
that all that testing that you were talking about, that was being done at the Goddard Space Flight Center in Maryland.
Okay, I was close. It was Maryland.
Yeah.
At least it wasn't Texas or something.
Just outside of District of Columbia.
Hey, speaking about telescope issues and things, Bob asks if we have any input, I guess, on the Hubble troubles.
Yeah, it sounds pretty bad.
Yeah, it does sound pretty bad.
So look, the for those who weren't aware, the Hubble has had a very serious computer problem for going on nearly a month now, right? And what happened is the main control computer started to fail, and the main control computer has 3 memory boards. There's a lot of redundancy on the memory. They thought it was a bad memory board, but then they discovered that the computer was doing the same thing, which was not working, regardless of which memory board it was using. So the plan was, let's switch to the backup computer, which hasn't been fired up for 40 years. And we'll see whether the backup computer controls the telescope properly. Before they just hand over control of the telescope to a backup computer, they have to run through all of these diagnostics on the backup computer to make sure it works properly before they say, okay, now you could drive the car. And apparently the same faults that they're seeing on the primary computer are also being seen on the backup computer, which is suggesting a problem upstream from the computers themselves. It could be power, it could be something else that's getting in the way of these systems functioning properly. But the articles I'm reading about this are beginning to sound more and more like obituaries than they are like solutions, but there's still more stuff that they want to try. They haven't given up yet. So I'm not going to be completely pessimistic about it, but it doesn't sound good.
Are you
And of
sure
course,
it's
yeah.
Are you sure it's not just a Windows 11
Yeah.
beta test?
Right.
It's trying to do an update
Yeah,
and it can't.
yeah. It's Windows 11, folks. Be careful. You might end up like the Hubble. Yeah. So if they can't solve this problem, there's not even any partial use for the Hubble. They will just send the signal to deorbit it early, and that'll be that. I guess it's pretty good timing to have this thing fail right before they get the Webb launched, and at least you're immediately moving on to something else. But I hope they can fix it. I mean, it would be pretty amazing to get a 40-year-old's backup system in place and operational to continue using the scope, but who knows?
Uses a 286 computer or something.
I don't even think it's that recent. I mean, these are computer systems that were designed in the 60s, right? It's probably like an 8088.
Yeah, right.
I'm not sure. It's a good question. I'll have to look that up. Yeah, right. Or it's a Z80 processor.
Right.
Well, that's all I got for tonight.
All right. Well, let's see. We're almost up to 9 or 10:30 here.
Yeah, let's go to questions then.
Yeah.
Michelle asks, will it crash into the Pacific? I'm not sure where it'll crash. Depends on what happens or when they decide to deorbit it.
Yeah, it will be an ocean. It will be an ocean deorbit.
Yeah.
They'll do it controlled in such a way that they'll know where it's going to be. It's not going to be like some other countries, which will remain unmentioned, that just say, "Well, we'll just let it plummet.
We'll just let it fall."
Yeah. They'll pick an ocean. It will either be the Pacific or the Indian Ocean, probably. And
unfortunately, we won't be able to recover the mirror and use it again.
Yeah, tell me about it.
I was just thinking we could capture the thing and install it at Chabot, and then we'll have a fourth telescope.
We could turn Nellie into a binocular telescope.
Yeah.
All right. Any other questions?
Oh, Bob Schock said it was an 80, that the processor was an 8080. So I was close. I said 8088.
Yeah. Yeah, that was launched, in 91, right?
I think so.
Yeah.
But it had been designed much earlier than that.
Yeah. The first service he mentioned was in 1993, so I think it was launched in 91. Yeah. And then I saw something from Tim. He said that core collapse takes 1 second.
1 second or less.
Geez.
Yeah.
Boy, I don't know where I was thinking that there was a longer process that was a prelude, but that was all in my imagination.
There were some questions that already got answered by other people on the thread here. Do supernova explosions produce gravitational waves that we can detect? And
that is an excellent question, and the answer is yes.
Well,
yes,
Tim says yes, they produce gravitational waves that we can detect. No.
Well, no,
not sure about that.
LIGO detected the result of, well, I guess it really wasn't a supernova, but it was
there was a neutron star collision.
Neutron stars,
much more energetic.
Yeah, it was two supernova remnants essentially that collided, and we were able to detect that. So yeah, that's a little bit different.
But a supernova does produce very strong a flood of neutrinos, which are hard to detect, but you can detect them. And it also produces gamma rays, which we have a lot of methods for detecting those as well. So it's not like we can't see it or detect it when it happens. But the gravitational waves are a little too weak, I think, to be detected by current technology.
I do want to point out that although they probably can't say they've done it yet, it is one of the missions of LIGO, which is the Gravitational Telescope. These are these large telescopes that are designed to detect gravitational waves, and they're not telescopes like anything you would recognize. They're like, yeah,
they don't look like telescopes.
They don't look like telescopes. But part of their core mission is to detect core collapse supernova. But no one can say that they've been able to do so yet.
All right. Any other questions?
Got anything on YouTube, John? Let me see if I.
No, a few comments here and there, but not very much tonight.
Oh yeah, lots of brief comments.
Everybody's getting warmed up for the 4th of July.
I guess, yeah. All right. Well, we covered a lot of ground, a lot of space.
Yeah.
So maybe we'll have better luck next weekend with the weather.
Next weekend, I'm going to try a little experiment and show how to observe Venus in the daytime.
Oh, cool.
We'll see if we can get some of our listeners to try that.
Oh yeah, that would be good.
Hey, we want to remind everybody once again, the Chabot Space and Science Center is currently closed. We are doing lots of renovation of the interior. There's going to be some new exhibits, part of our NASA partnership, and some new programs and so on. So we do still need your support. So if you can take a last minute stab at that donate button on the Facebook page, or go to the Chabot website, which is chabotspace.org, and click on the donate button at the top of the page there and help us out. We would really appreciate it. If you work for a company or you know of a company that would like to get their name on our program as a sponsor, there are some instructions on the Chabot website for corporate donors who want to work with our development people to do that.
Great. Thanks, Charles. All right, guys. Well, enjoy the rest of your weekend. And,
have a great 4th of July, and try not to burn the house down.
Yeah, that's the main goal.
Right.